James Clerk Maxwell, the master of electromagnetism, wrote in his great work, A Treatise on Electricity and Magnetism. The magnetic force acting on a current in a conductor does not cause any deflection in the current itself. It acts on the conductor, not on the current. However, Henry Augustus Rowland viewed this from a different theoretical perspective. He reasoned that if an electric current were the flow of charged particles, then a magnetic field should deflect these particles. He presented this idea as a question to his student, Edwin Hall. Hall's initial idea was straightforward. Take a wire, pass a current through it, apply a perpendicular magnetic field, and see if the current or electric potential distribution changes. But the experiment encountered great difficulty. He tried using probes to measure the electric potential at different points along the wire. However, due to the low purity of materials, such as iron, copper, and other metals at the time, the intrinsic potential difference caused by material inhomogeneity was far greater than the tiny effect he was trying to find caused by the magnetic field. The signal was completely drowned in noise. Professor Rowland gave him a crucial suggestion. Abandon the wire conductor and use very thin gold foil instead. Hall adopted his mentor's advice. The core part of his experimental setup was as follows. Material, a very thin sheet of gold foil. Current, a steady current, passed along the length of the foil. Magnetic field. A strong electromagnet produced a magnetic field perpendicular to the plane of the gold foil. Measurement. Probes were soldered to the edges on both sides of the foil, perpendicular to the current direction, and a highly sensitive galvanometer was used to measure the potential difference between these 2 points. When the electromagnet was powered on and the magnetic field was established, the needle of the galvanometer clearly deflected. When the magnetic field was switched off, the needle returned to zero. This transverse potential difference, later called the Hall voltage, unequivocally existed, and 1. Its magnitude is proportional to the current intensity. 2. Its magnitude is proportional to the magnetic flux density. 3. Its direction depends on the directions of the magnetic field and the current. The classical Hall effect can be divided into 2 types based on the type of charge carriers, N-type and P-type. 1. Untyped Hall effect. Typical material. Intrinsic semiconductor, for example, silicon germanium doped with a small amount of donor impurities. For example, phosphorus, arsenic. These impurity atoms have one more valence electron than silicon, making it easy for them to release an extra electron. Majority carriers. Free electrons, negatively charged. Minority carriers. Holes, positively charged. Conductivity. Primarily formed by the movement of negatively charged electrons. Therefore, N stands for negative charge. 2. P-type Hall effect. Typical material. Usually, an intrinsic semiconductor, for example, silicon. Germanium doped with a small amount of acceptor impurities, for example, boron, indium. These impurity atoms have one fewer valence electron than silicon, creating an electron vacancy that can accept an electron. Majority carriers. Holes equivalent to a positively charged particle. Under the influence of an electric field, a neighboring electron can jump into this hole, causing the hole to move through the lattice, which macroscopically is equivalent to the directional flow of positive charge. Minority carriers. Electrons. Conductivity, primarily formed by the movement of positively charged holes. Next, let's introduce the Hall effect experiment apparatus developed by Brolight technology. This apparatus consists of a power supply, a switch module, a Hall sensor, and a coil that provides the magnetic field. The Hall effect experiment apparatus, designed by Brolight technology, perfectly recreates the experimental process of Hall's original discovery of the Hall effect. Our Hall sensor uses a metal foil similar to the one Hall used in his experiment. Very fine gold wires are used to connect to the measurement points on the semiconductor wafer. With our Hall effect apparatus, you can not only investigate the relationship between the working current and the excitation current, i.e., the relationship between the magnetic field and the Hall voltage, but you can also change the measurement points on the Hall sensor using the switches on the switch module. Use this switch to measure the conductivity of the Hall sensor. Then, by toggling the switch, you can select either a P-type or an N-type Hall sensor. You can visually observe the change in Hall voltage produced by the 2 different types of materials. One is the Hall voltage generated by electrons. The other is generated by holes. Hall effect applications are widespread in daily life and industry, primarily categorized into 1. Measurement and detection. Measuring magnetic fields, Tesla meters, Gauss meters. Measuring current, non-contact current sensors used in electric vehicles, solar inverters. Measuring position, automotive, pedal, valve position, liquid level height. Measuring speed, automotive ABS, wheel speed, motor rotational speed. 2. Control and switching. Contactless switches, car door, laptop lid detection, proximity switches. Motor control, core component for commutation, in brushless DC motors, drones, hard drives, fans. 3. Semiconductor industry. Material analysis. Determine if a material is N-type electron-rich or P-type hole-rich, and measure carrier concentration and mobility. 4. Cutting-edge and specialized applications. Magnetic storage, early hard drive, read heads for data reading. Aerospace propulsion. Hall thrusters, ion propulsion, for satellites, space stations. Metrology standard. The quantum Hall effect provides an absolute standard for electrical resistance. The scientific exploration of the Hall effect never stops. That's all for this science episode. Thanks for watching.